4 minutes to the program, a couple of reminders, please. Number one, please silence your cell phones.
Good afternoon. Welcome to the Johns Hopkins Applied Physics Laboratory in Laurel, Maryland. I'm Mike Buckley from APL's Office of Communications and Public Affairs, and what a week it has been for exploration. NASA's New Horizons spacecraft conducted the farthest flyby in history, speeding past the Kuiper Belt object nicknamed Ultima Thule. And mission scientists have been making all kinds of discoveries in the images and measurements that New Horizons has been sending back. Now, we've managed to pry some of those scientists away from that data for a little while to give us an update. So with us today is Alan Stern, Principal Investigator for New Horizons from the Southwest Research Institute, Mark Showalter, New Horizons Co-Investigator from the SETI Institute, Leslie Young, New Horizons Co-Investigator from Southwest Research Institute, Silvia Protopapa, a New Horizons Co-Investigator from Southwest Research Institute, and Paul Schenk, a New Horizons Co-Investigator from the Lunar and Planetary Institute. So each of the, we will have information from the science team members, and then we will take questions from the media here in the auditorium and also on the phone lines. So first we'll start with Dr. Stern.
Thank you, Mike. Well, what a week it has been, indeed. And we're going to make 4 presentations by my 4 colleagues to my left on new scientific results for you. But since this is our last opportunity to speak with you during Flyby Week, I thought I would give a little update on the spacecraft and our status. And then I want to say a little something about the mission and putting what we have done in context. Regarding the spacecraft, New Horizons is now already about 3 million miles deeper into the Kuiper Belt than Ultima Thule. And the spacecraft this morning conducted its last observations of our flyby target and then successfully transitioned out of the flyby command load and is now operating on its first command load of the new year. That command load is already going to be making observations of the deeper environment in the Kuiper Belt and making observations of other KBOs in the distance. Now with that, I'd like to take you back to 2015. You know, we launched New Horizons in 2006 and flew 9.5 years to cross the solar system. And our first target was the king of the Kuiper Belt, the planet Pluto. And here you see this beautiful picture of Pluto made in enhanced color as a New Horizons data product. The target that you see there is about 2,400 kilometers in diameter. And why don't we just zoom up on Pluto so that you can see it in a little bit more detail. We're going to go right down on the deck on a place called Sputnik, which is a nitrogen ice glacier. And you can see the complexity in that planet, but in addition, I want to just show you the difference in scale between Pluto and Ultima Thule, our second flyby target. And you'll see it pop up right there. Wow, isn't that a difference? This is the difference between a planet and a planetesimal. And it's also something that I think viscerally indicates just how much harder it is to navigate to such a much smaller target than Pluto. So with that, having given you this background now and told you where the spacecraft is and what we're doing, I'm going to hand it off to my colleagues. We'll start with Mark Showalter, but before we do that, you might have noticed these 3D glasses. My colleague all the way down to the left, Paul Schenk, is going to be presenting the very first stereo imagery of Ultima Thule. And if you have glasses like this at home, you might want to take a sec to just grab them. And if you don't have those glasses handy, this presentation will be on the web and you'll be able to access it later. Okay, and with that, I'm going to hand it off to Mark.
Thanks, Alan. I'm here today to talk a little bit about our search for moons of the Ultima Thule system. As you all know by now, there are actually essentially 2 bodies in the system, Ultima and Thule. So if we've seen now bodies 1 and 2, the question is, well, what about bodies 3, 4, and 5, and so on? I'll give away my answer right now, which is that we have not found any other moons, any bodies in the system beyond the 2 that you see here. However, we are looking, and we're looking very hard, and we are looking for some very good reasons. This is a slide that Dr. Jeff Moore showed you yesterday. It describes our formation understanding of the system itself. On the left, you see that we had in the distant past a swarm of small bodies, and those eventually coalesced into the 2 bodies, Ultima and Thule, but at the time they were in orbit around one another, around their common center. And over time, they came together and touched gently. Now, there's a puzzle with that, which is that at the time they touched, they were probably rotating much faster than they are today, probably in 3 or 4 hours, rather than the 15 or so hours that we know about today. So how did they slow down? Well, the best way to understand that is if there were another moon, or 2 or 3, orbiting this system, essentially what those moons would do is put the brakes on the two bodies in the middle, slow them down, and as a result, the small moons would spiral outward a little bit, but not necessarily very far. So we're looking for the objects to put the brakes on this object so that it isn't spinning today as fast as it was originally. Now that would also be a really important result for us because we don't know and are going to have a very hard time finding out what is the interior of this particular object. We will see the outside just fine, but knowing its mass and knowing its density is the key to understanding its interior. And to get that, the best way to do it is to find an object orbiting these two. So with that in mind, let me give you an illustration of what we've been doing. If you go back, it's hard for me to remember this, but only about a week ago, what you're seeing now is the best image we had of the Ultima Thule system. What you're really seeing, of course, is a star field. Ultima Thule is in front of the galactic center, and we needed to do long exposures to see Ultima Thule itself. Any of those long exposures also picked up a very, very large number of stars. And that is, of course, very challenging, but we on the team, some of our members have derived some really fascinating and very powerful techniques for cleaning up these images. And essentially what you do is subtract one star field from another, where one star field has Ultima Thule in it and the other does not. And when you do that, you get something like this. And although maybe the last 100 or so stars have been left behind, you can now clearly see Ultima Thule in the middle. You see some scattered light and various other artifacts, but we're looking for dots. And a moon would be understood to be seen as an extra dot that is persistent from one image to the next to the next. And so far we have not found any dots, but if we did, that would have to correspond to a moon that's about 1 mile across and about 500 miles away from Ultima Thule itself. We've had another opportunity to look in a little bit closer recently. This is the image we released yesterday, and as you can see, it's a, you of course saw the snowman figure, but there's a field of view around that, and when I pump up the contrast on that particular image, what you see is this. And most of those dots are stars. There's a few others that are cosmic ray hits, but we know that and we can recognize that. The reason that you don't see all the stars that you saw previously is that this is a much shorter exposure. But we've examined images like these, and when we do that, we determined that an object about a few hundred yards across, say the size of a few football fields, would be visible in these images, and nothing has been seen. So, of course, to be in this image, it has to be within about 100 miles or so of Ultima Thule itself. So there's a gap now where we could see things within 100 miles of Ultima Thule. We can see things beyond about 500 miles from Ultima Thule. And there's a gap in between where we have not yet been able to do a thorough search for moons. So that opportunity is coming. We have to be a little bit patient because those images are still in the spacecraft. But within a few weeks, we will be seeing them, and we will be able to complete our search for the moons of Ultima Thule. Thank you. And now the next speaker is Leslie Young.
Thank you, Mark. So I'm on the atmospheres team for New Horizons, and I want to remind you of the summer of 2015, good times, when we flew past Pluto. It has a thin atmosphere. It's about almost 1 million times thinner than the Earth's atmosphere. It's like being up in our stratosphere, but it's very extended. The top of the atmosphere that we were able to measure at Pluto is about a Pluto radius above the surface. And we could measure the atmosphere at Pluto very easily with the ultraviolet spectrometer ALICE and with our plasma instruments. This is a figure showing how we were able to detect the slowdown of the solar wind as New Horizons flew past Pluto. And for scale, over on the right, we have the United States. So that shows you that the extent of the atmosphere on Pluto is about as wide as the entire of the United States. And again, for scale, the United States is about the distance that we flew from Ultima Thule, our target from last New Year's Eve. Ultima Thule itself is very small, only about 20 miles across. And the lines that we're showing are a schematic of the solar wind blowing past the small body Ultima Thule. Now zooming in on Ultima Thule, which is the tiny double dot at the bottom of the scale bar, we don't expect to see a slowdown of the solar wind the way we did at Pluto. We expect to have Ultima Thule just block the solar wind. We don't expect to be seeing any atmosphere coming off of the solar wind to detect dust, but spacecraft missions, it's all about exploration. So you gotta try. We're only flying past Ultima Thule once, so we looked with everything we had. And the next animation is going to be an example of one of our prime observations. This shows the spacecraft as it flies past Ultima Thule, turning the antenna and the solar occultation channel of the ultraviolet instrument ALICE back toward the Earth to, for instance, watch the sun as it gets filtered through an atmosphere around Ultima Thule, if there is one there to see. So here it is, just a couple days after we flew back. We have down on the ground some of our atmospheric dust and plasma data. We have a couple hours of data from the ultraviolet instrument staring at Ultima Thule. We have a few hours also from the plasma instruments. We have about a day's worth of data from the dust camera. We looked back at Ultima Thule with our imagers, with MVIC and Lori. Those are not going to come back for a few weeks, but when they do, we will look to see if we see dust entrained in a coma the way you might see it on an outburst from a comet. So we're looking forward to this data, and even if we don't detect any atmosphere or plasma or dust, these are very important measurements because Ultima Thule is there exposed to impacts from its environment, from the energetic particles from the plasma of the solar wind, from the energetic photons in the ultraviolet, and that affects its surface. You've heard earlier in the week that the surface of Ultima Thule is dark and red, and the secret to the processing of this body and other bodies like it is probably going to lie in the plasma, energetic particle, and ultraviolet environment. And to tell us more about the color, I turn to my colleague, Silvia.
Thank you, Leslie. So the panel on the left shows the architecture of the solar system. The orbits of the giant planets are shown in magenta, while the trajectory of the New Horizons spacecraft through the solar system is shown in yellow. Beyond the orbit of Neptune resides a population of objects, the Kuiper Belt objects, up to 50 astronomical units from the Sun. The cold classical Kuiper Belt objects are a particular kind or dynamical class because they reside in a tight ring on near circular, low inclined orbits. We believe that this dynamical aspect of cold classical Kuiper Belt objects is due to the fact that these objects were not perturbed by the giant planets, contrary to other dynamical classes in the Kuiper Belt. So the term cold does not refer to temperature, although these objects are very cold, but instead refers to the primitive aspect of this population. The panel on the right shows the redness of Kuiper Belt objects as a function of orbital tilt. The cold classical Kuiper Belt objects are shown in red, while the rest of the population is displayed by yellow dots. As you can see from this plot, cold classical Kuiper Belt objects are relatively redder than the rest of the population. Ultima Thule is represented here by the white dot, and it displays an average color that falls well within the average colors displayed by the cold classical Kuiper Belt objects. This implies that Ultima Thule is well representing this dynamical class, this population of objects that are primitive. And therefore, the detailed measurements that we will perform in the next weeks, months, years, will provide the context for understanding the composition and formation of these objects. The image I'm showing here is the enhanced color image taken by the multispectral visible imaging camera obtained combining the blue, red, and near-infrared channels. Quantitative analysis of the color of this image indicates that the average color of Ultima and Thule, the two components of this bilobed object present the same average color. This tells us something important about the formation of this object. In particular, we believe that this object is a contact binary resulting from the merger of two objects formed close by to each other in the protoplanetary disk. This is supported by the evidence obtained with the ground and space-based measurements of binary systems in the Kuiper belt. In particular, what we have found so far is that the primary and secondary component of binary systems in the Kuiper belt present the same color, therefore supporting our theory of the formation of this object. And with this, I will lend it to my colleague, Paul Schenk.
Thank you, Silvia. One of the main objectives for New Horizons at Ultima Thule is to determine not only the shape and size of this body, some of which you saw yesterday, but also the relief of geologic features on its surface. And in order to do that, we needed to acquire resolved stereo images of the surface. Now, this is our first stereo anaglyph of the surface, and you can put the red-blue glasses on now. It is our only stereo view, but we're expecting much better stereo images as the data are downlinked and returned to Earth. Now, if you don't have red-blue glasses, be patient. We're going to show alternative versions of this in just a few moments. The two images have resolutions of about 300 meters and 140 meters, respectively, and do not have a lot of stereo parallax, but they definitely reveal the basic shape of Ultima Thule, and they do indicate that the prospects are very good for the planned stereo observations that we have coming down in the weeks to come. Now, there are alternative ways of looking at this view. You can see the basic round shape of the two lobes and the narrow neck. We can also split these images into two side-by-side images. This is suitable for viewing with ordinary stereo viewing glasses or by crossing your eyes, which may give you a headache if you're not too careful. This pair was actually put together by astrophysicist Dr. Brian May, who some of you may know as the lead guitarist for the band Queen. He is going to release this image in the next few days on his website. Now, not everyone has stereo glasses or can view cross-eyed, so he put together this view, which blinks between the two images and gives you a sense of not only the shape of the body, but the rotation that New Horizons is seeing on its approach. Now, you see a bunch of things in this view. You see obviously how narrow the neck is between the two bodies. You also get a sense, at least, that the bright material may be concentrated in topographic lows. And this may indicate downslope movement of material from topographic highs, such as ridges. And there's an indication that the dark stripy materials that we see may actually be topographic ridges as well. So we can't really wait to receive the final images in order to determine whether this is, in fact, the proper interpretation. You may also notice along the upper right-hand margin that features appear to be rotating into view as the object twists underneath us. These have a knobby appearance and could be the inside of a large impact crater that's on the far side. They could also be small accretionary lumps or something we haven't even thought of. This area, as I said, would be rotating more into view in the images that are going to be downlinked in the weeks to come. We do need to be careful about interpreting images like this because these are basically equivalent to full moon images that we see from our Earth, where shadows and textures are washed out and we see albedo variations. So some of these markings could be ridges, but we won't know for sure until the subsequent images are downloaded. We do expect to see much better views, including stereo, of the neck region. And the very best images, Ultima Thule, should, in fact, basically fill the camera frame. So it should be very interesting indeed. And back to you, Alan.
Okay, thanks for that. Well, I'm going to close this out by telling you a little bit about what's next for New Horizons and our exploration of Ultima Thule over the next couple of weeks. But before I do that, I want to do something that I think is a little bit special. I know for a lot of people, when you think of a space mission like New Horizons or others, you think of engineers and scientists and flight operations personnel and lots of math and lots of computers, and that's certainly the case. But there's a broader aspect to what we do as well, and in fact, we actually, in some cases, use art to help illuminate the science. And I want to highlight the work of 3 members of our science team who actually are doing just that this week to help us explore what all this data means. And so here with me, to my right, are James Tuttle-Keene of Caltech, and then Leila Gabasova of the University of Rhône-Alpes in France, and then Mallory Kinzich of North Carolina State University. And as I said, each of them is applying art in a different way, and let me illustrate that. This is one of James's drawings in which he's illustrating artistically, making hand sketches of the kinds of processes that may be taking place on the surface of Ultima Thule and that are indicative of the data that we're receiving. And then secondly, are we on that slide? Yeah, okay. We lost our monitors. So secondly, I want to highlight Leila's work in which she's sketching individual members of our team and making drawings that tell a little bit about what each person is working on. And then finally, Mallory's work is this wonderful model that we now have, a 3-dimensional model that actually represents the object for us in a physical state. And I think this is really special stuff, and I would appreciate if the audience here in the room at APL would give them a round of applause. Great. Well, let me just say a few words about what's next. Beginning tomorrow, in fact, the spacecraft, as seen from the Earth, goes almost directly behind the sun. And the sun's outer atmosphere produces a kind of radio interference that doesn't allow us to transmit imagery and spectra to the ground. So there's going to be a pause in that downlink for about 5 days until the 10th of the month, the 10th of January. And then the data will start to come back down again and begin this long 20-month period in which we'll be emptying the solid-state recorders of all of the different kinds of data that we've taken, literally hundreds of images and spectra and other data types. Now, also during that time, the science team is going to be pretty hard at work. Even while the spacecraft is behind the sun, the science team will continue to work on the data that we have, and then beginning the 10th, as these new data sets land, we're going to dive into those. And then we meet 2 weeks from now as a science team in mass to review those results, and I expect there'll be some pretty good news, so you'll be hearing from us again in a little over 2 weeks with those additions to what we've already learned about this wondrous place, Ultima Thule, and this wondrous, scientifically valuable region of the solar system, the 3rd zone called the Kuiper Belt. And with that, I'll turn it back over to Mike.
All right, thank you. We'll start with questions here in the auditorium, and then we'll check to see if the phone lines are too. So we'll go right here.
Hi, thank you. Ken Kramer, Space Up Close, Northeast Astronomy Forum. Well, first, congratulations again on spectacular results. So now you have a little bit on the composition and the color. I wonder if you could say, you said the color was uniform. Do you think that means that the composition might be uniform between these two bodies? And what else can you tell us about the composition? Is it uniform, and what would be the constituents based on the data that you have now? And any cratering, Alan, do you think there's a crater there now? Thanks.
Do I think what?
Is there a crater? Now that you have the 3D, do you see craters or not? Thanks.
Okay. Well, I guess I'll take both questions. First, I ought to caution that we're going to see Ultima in much higher resolution. And you saw in the black and white, the panchromatic images, that we do see variations in the surface albedo from place to place, like those white structures, both the linear ones as well as the more oval-shaped ones on the surface. And one of the interesting things that we want to do when we get higher resolution color and composition measurements is look in those places that are brighter and darker and see if there's a correlation. Right now we only have our very lowest resolution color, and we don't even have a complete spectrum of the surface. But we will have that, and at that time I think we'll be able to make a definitive statement about the level of variations in composition across the surface. I would caution you not to use the very low resolution that we have now and conclude that there are no variations, because we can only currently talk about color and composition variations at this low resolution. And then regarding your second question, I'm going to stick to the advice of my stereo experts who tell me that at this phase angle, you really can't trust the topography. And so we'll wait and see again for higher resolution data. I'm very excited to see that and look at the number of craters and what that has to tell us, not just about the surface of Ultima Thule, but about the bombardment environment and the collisional environment that it's in and where it was formed.
Okay, we'll stay here in the auditorium.
Marcia Dunn, Associated Press. You mentioned ridges that have been spotted. How deep or tall, or what, could you give some estimate or guess as to how pronounced they are? And also the slopes going down toward the neck area. What kind of an angle are you thinking that really is for sled riding or something? Could you know, just give us a little comparison of how steep that is?
I guess that one's for me, but yeah, we think we're seeing what could be interpreted as ridge structures. Primarily those that are darkest, they appear in the stereo, which has a weak parallax, so it's not the optimum view. They look like they're high standing, and we see somewhat similar features on other icy satellites, but we really don't know for sure until we get higher parallax angle on them. But we do know from the limb profiles that, I think we showed those yesterday, is that right? But we can actually measure the relief along the limb, and we get a couple hundred meters variation, which suggests that maybe those ridges, if they do exist, are that amplitude. But we're going to have to get back to you on that one in the weeks to come. As far as the slopes on the neck, I think we may have estimates on those, but I don't really remember. But they're basically similar to the roundness of the sphere, so they're comparable to that. I don't remember off the top of my head. We can get that for you later, I think.
Okay, we'll take one more question in the auditorium, and then we'll go to the phones.
Hi, Ken Chang, New York Times. I had a question about things coming up. The high-resolution images at closest approach. I know they'll come down later, but do you have enough knowledge about the trajectory in the closest flyby to know whether you got them?
Yeah, we don't know that yet, Ken. In order to get that, we're going to have to analyze the images that we have in a little bit more detail. But more importantly, we have to get down some engineering data that tells us about the pointing, and we have to get our next trajectory reconstruction, the post-flyby, the first post-flyby trajectory reconstruction. And to get all those steps is going to require a couple of weeks of work after we get out of that solar conjunction that I was talking about. At that point, we'll be able to calculate where in that long train of hundreds of images we will find Ultima, and then in place commands in a command load for February to download only those that contain the target.
Okay, so from here we'll go to the phones. We have a question from NASAspaceflight.com.
Yes, Chris Gephardt from NASA Spaceflight. For Alan, yesterday you had mentioned that a lot of the data that New Horizons has collected both at the Pluto system and at MU-69 is being fed into our various models of how the solar system developed. And I was just wondering if there's anything that you've seen so far from the totality of the mission that would speak toward the accuracy of the NEAS model of solar system development, and how Uranus and Neptune really perturb the Kuiper belt. Are you seeing anything that confirms that or leads you away from that? Or and is it still fair to say that those two giant ice planets are the main reasons why the Kuiper belt didn't really accrete into something more significant than we see in the planets that are there?
Yeah, I think that's a very good question. I think that our best handle on that is going to come from an understanding of the ancient primordial size distribution of these impactors. And we've got that information on the satellites of the Pluto system and on Pluto's surface itself. But because Pluto, its satellite system was formed in a giant impact, and for other reasons as well, the crater size frequency distributions that we derive in the Pluto system may not be representative of this era. And so I think Ultima is really the place where we're going to get that information, and we're really looking forward to it.
Okay, we can go back to the auditorium for any questions here.
Hi, Chris Lintott from BBC Sky at Night. Thinking about the formation model, we seem to have a process that produced two roughly spherical objects, which then collided and didn't produce a spherical object. Do we have any idea why that last collision would have been different?
Mark, you want to take a crack at that?
I'm sorry, could you repeat the question? Yeah.
So whatever process assembled the two bits of Ultima
Yes.
Thule produced roughly spherical objects, but then the final collision, which is presumably part of the same process, produced something that wasn't a sphere. So was there something different about that last collision, or did it just run out of material, or why do we end up here instead of a larger spherical object?
Yeah, there's a couple of possibilities here. We've done a lot of simulations where you see a swarm of bodies, and then just numerically we let that whole process play out. Very often, a very common scenario is two objects in the center and a few more objects outside. Now, the long term, there is often this end state that we see here. Sometimes it's two objects that never touch each other. Sometimes they do come together. But for them to come together, you have to carry off what we call the angular momentum. And so that's, if there are external satellites, that's when you tend to get objects like this, binaries, but sometimes those satellites keep going. They just escape completely, and you would never see them. So it's quite possible that we will never actually see the culprit that is responsible for example, the slow rotation of Ultima Thule, because it's gone now. It was there before, or maybe it was multiple bodies, but they've all escaped.
Okay, we'll do one more question here, and then we'll go to the phone lines.
Charles Clark, Joint Quantum Institute. Just a question on nomenclature. Today is the first time I've seen Ultima Thule used as a compound noun composed of apparently the two bodies. So which is Ultima and which is Thule? And will this be submitted to the International Astronomical Union for ratification?
I'm glad you asked that question. Remember that the term Ultima Thule is an informal name that we're using because it's a lot easier to say and remember than 2014 MU69. Once we arrived and we were able to see that this was a bilobate object, we gave each of the lobes a part of the name. The larger one is Ultima, and the smaller one is Thule.
Go to the phones. We have a question from Sky and Telescope.
Hey, thanks a lot. This is for Silvia Protopapa. If I can make a leap and say that maybe the brighter areas are exotic ices. I love saying exotic ices. Might you expect them to be the same as you found on Pluto, carbon monoxide, methane, nitrogen, and will you have the spatial resolution to detect them individually on the body?
Thank you for your question. So in general, yeah, you are right. We found on Pluto a surface that is covered by organic materials, water ice, but also exotic ices like methane, nitrogen, and carbon monoxide. Ground-based measurements of intermediate objects, much smaller than Pluto, do not display any presence on their surfaces of any exotic ice. Instead, they present surfaces covered by organic material and possibly water ice and ammonia. We will look on Ultima Thule surface for any kind of organic materials, water ice, but also exotic ices. We do not expect them, but we will look for it, and we will have the spatial resolution to identify these ices, if any.
Okay, we can stay on the phones. We also have a question from space.com.
Thanks, Scott. Thanks, guys. Mike Wall from space.com. This one's probably for, I guess, Alan. Like you mentioned briefly what you're already doing, like kind of looking ahead and putting a new command load for what lies beyond Ultima. And yeah, could you just go into a little more detail about what those commands are and what you're looking for now that you've passed it and it's in the rearview mirror, and what you're looking for now as you go deeper into the Kuiper Belt?
Well, I'm sorry to say this, but I found that kind of a garbled, not your question, but the audio is garbled. So if you could say that a little more slowly.
Sure. Yeah, sure. Sorry. Can you hear me okay?
Yeah, that's better.
Okay. Yeah. Like I was just wondering, Alan, you just mentioned that you're on a new command load now, going out deeper into the solar system, like deeper out into the Kuiper Belt. I mean, could you just kind of go over briefly what that command load is, what sort of observations you're sort of planning to actually make in the coming weeks and in the coming months, and what's coming next in terms of the science, but that goes beyond Ultima?
Yeah, so if I follow you, Mike, what you're asking about is what kind of observations we're going to be making over the coming weeks and months out deeper in the Kuiper Belt. And so they really fall into two categories. First, we use our in situ instruments, the two plasma spectrometers and the dust instrument, along with the ultraviolet spectrometer, to study the local environment of the Kuiper Belt. We think of ourselves as making a transect outward from the sun on this straight line trajectory that we're following, all the way from the inner edge of the Kuiper Belt, where we were in 2014 and 2015, out to a distance of 50 astronomical units, which is the far extent of Pluto's orbit, where we'll be in 2021. And those measurements take place almost 24/7 with the plasma and the dust instruments. The ultraviolet spectrometer is used to study the distribution of neutral hydrogen in the Kuiper Belt, and we do that a couple of times a year by making some maps. And so, as Leslie told you, this radiation environment, radiation, gas, and dust environment, is what's responsible for the space weathering of the surfaces of not just the Pluto system, but all these small planetesimals like Ultima Thule. And so if we want to understand how those surfaces evolve by interacting with the environment, we have to understand what the environment is and how it varies from place to place in the Kuiper Belt. And so we'll resume that. In fact, we're resuming that today. And as I said, it goes on almost 24/7. But then we also use our LORRI telescope and camera to look in the distance at other Kuiper Belt objects to make context studies of them to compare to Ultima. So for example, we photograph those objects over and over to watch how their brightness varies and determine their rotation periods. And when we're close to them, not as close as we went to Ultima, they're all just dots in the distance, but we get close enough that we have better resolution than the Hubble Space Telescope, which is way back here at the Earth, because of our proximity to the targets. And so we can look for satellites of those targets in ways that you can't do from the Earth. And there are other studies that we make as well. And we're doing a little bit of that this week with a couple of KBOs that we're relatively close to right now. Still thousands of times, actually tens of thousands of times further away than we were to Ultima, but close enough for us to do useful things. And the next opportunity to do that is going to be in March, and then we're going to do some more in the fall, and then we'll pick up with even more next year.
Okay, I'll stick to the phone for one more before we come back here, and this is from Business Insider.
Thanks for taking the question. So now we know there are a lot of big red snow people, as it were, in the Kuiper Belt. I just have a bigger multi-part question here. How many of these might be out there, and by what percentage of the solar system would attach to that? Can you say what number or fraction have gone into forming the large, sort of larger inner planets of the solar system? Just trying to get a bigger sense of where the...
Who would like to take that? Yeah, that's a dangerous question, but go ahead, Leslie.
Well, there's about a dozen other Kuiper Belt objects that we think are contact binaries. That's a first tiny piece of the project. Obviously, the way to tell for sure if something is a contact binary is to send a spacecraft to it, as we did with New Horizons. From the Earth, we're limited to much more difficult observation over the course of a season or several years. If it were aligned so that the rotation was sideways, you would see most of the time both bodies, and then every once in a while one of them would block the other one very well, and you would get a sharp drop. And so from that, people think that they have seen other snowmen in the Kuiper Belt, but we won't know for sure until we're able to visit them.
I'd like to make one addition to that story, and it's related to something we did on New Horizons that we spoke about earlier in the week, and that was the stellar occultation that we did of Ultima Thule to determine its shape in silhouette back in 2017. And we showed you yesterday just how accurate a silhouette we got compared to the actual target. So now that we've developed these techniques, and this is again due primarily to the work of Dr. Mark Bowie on our team, really state-of-the-art work, that we can see these very small bodies in silhouette from such a great distance and predict when these stellar occultations will occur and successfully deploy teams to go and capture that data. We now have a zoom lens, if you will, on KBOs that will allow us to determine the shapes of objects that we could not see the shape of with the Hubble or with any ground-based telescope, even any ground-based telescope that's on the drawing board. So we really have a very powerful tool developed as a result of New Horizons that can be employed over the coming years to determine how many of these snowmen are really out there and what fraction of the objects we look at are in this contact binary mode versus orbiting alone or orbiting with satellites. I'm really looking forward to that work.
Okay, so we'll be here in the auditorium for questions here.
Hi, Bobby Russell with Quest for Stars. One of the most compelling images from the 2015 flyby of Pluto was the solar occultation. When might we expect to see some of the occultation images come down, and what do you expect from them?
So you might be confusing the solar occultation data, which is the squiggly line data from the ultraviolet spectrometer, which isn't very pretty unless you love ultraviolet spectrometers, to the beautiful images that we made with the Ralph camera and the Lori camera of hazes, particularly the ones with the blue ring, which was made at the same time that we were doing that solar occultation. And we did not take images like that of Ultima because it certainly doesn't have an atmosphere to the extent that Pluto does. And Leslie and the atmospheres team has already proven that that kind of a thick atmosphere that we never expected, in fact, doesn't exist.
But we did take high phase observations. So in those
for other purposes.
Yes.
Yeah.
Yep.
Okay, stay right here.
Hi, Christian Reddy from Launchpad Astronomy. I'd like to ask, you mentioned before about you have expecting further images coming up taken at a sharper phase angle or at an alternate phase angle. Can you tell us when you're expecting those images to arrive and elaborate a little bit more about what you're planning to see in them or look for?
For me? Okay. Well, those moderate and higher phase angle images are going to start to come down next month. And they're going to culminate with that CA06, the very highest resolution set that we've talked about so many times. But there are also some intermediate sets that'll come down as well. And some of them may even come down after because we're really trying to get the highest resolution data. We can't wait to get our hands on it. One of the things the science team is going to be doing in the next 5 or 6 days is putting in talk abstracts for the Lunar and Planetary Science Conference to report results in March. And we want to get those data sets to the ground so we can analyze them and report on them at that venue down in Houston.
Okay, so before then, we will finish up here in the auditorium. We'll go back to the phones for one more. I think we have a follow-up from Sky and Telescope.
Yeah, thanks very much. I appreciate the second question. Alan, can you tell us if the positioning of the Ultima Thule in your field of view of your cameras gives you confidence that the highest resolution Lori targeting will be successful?
Sure. I can't promise you that it will be successful, but I can tell you the fact that Ultima turned out to be precisely where we expected it to be in the handful of images that we already have on the ground is very reassuring. And had it turned out far away from where we expected, I think we'd be pessimistic, but I would say we are guardedly optimistic that those very highest resolution images will cover a massive amount of the surface. Stay tuned for February.
Okay, let's stay here. I think we had a couple more in the auditorium.
For Dr. Showalter, you're looking for moons. How long do you think that's going to, how long do you think it'll be before you can say, at least with, somewhat conclusion that there are or there aren't? And if there are some, how many would you expect to find?
Oh, I'm not going to predict the number. We'll be getting so as I mentioned, some of the close-up images already are pretty strict in their limits. And some of the most distant images, which are the ones that searched far out tens of thousands of kilometers or tens of thousands of miles away from Ultima Thule, those are the best images, and we've already got them to the ground. We actually use quite a bit of those images when we're searching for potential hazards. So we're not really going to push any further in those domains, but it's in between, which is actually probably the regime where we would most likely expect to find moons that we simply have not seen that data yet. Now, I know that it's beginning to come down in late January, so we'll have some preliminary results hopefully by late January. It's hard to promise then as well, but we will begin that process as soon as those images hit the ground, and those are the ones that I think if we find a moon or two, that's the data set where we would find them.
Okay, we'll take one more question here. We'll come back for another statement.
And a moon question too. I wonder if you find them out a little bit further, I think you said 100 miles further out, would that help you then figure out the mass and the density?
Oh, absolutely. Any moon at all, on any orbit at all, will tell us the mass and the density to pretty decent usable precision. And so we're very, very excited about that prospect. And that's one of the most important things that we would learn out of finding a moon. The other piece we would learn is whether it is the culprit that is responsible for breaking the rotation, reducing the rotation of Ultima and Thule around one another. When we have a mass and we have an orbit for some object in that domain, that's when we would start to get a little bit of a handle on that. It's possible that if we even find a moon, that it's not the culprit that caused the slow rotation, that in fact that was a different moon entirely, and maybe one that escaped or is somewhere else.
Okay, so I believe another, Alan, you had a statement you wanted to make?
Yeah, I just want to say one thing in closing as something Mike couldn't say and something that as the mission principal investigator, being from the Southwest Research Institute, where we built and were responsible for most of the scientific payload for scientific payload operations. I just want to say a big thank you to the Johns Hopkins Applied Physics Lab for building such a spectacular little spacecraft and for operating it so professionally for the last 12 years and for hosting the flybys of Pluto and Ultima Thule. And please join me in thanking them. None of the science or exploration that New Horizons is doing would be possible without all the members of our team, and it's a big team. But thank you again, APL.
Great. Thank you, Alan, and thank you, team, today for the update. New Horizons is on the web and on social media. You can follow all the progress of the mission at pluto.jhuapl.edu, on nasa.gov, on NASA and APL social channels. Like the team has said, this is just the beginning. I mean, it was an incredible week getting the mission started at the flyby, and now it's time to get into the data. So on behalf of the team, I'm Mike Buckley. Thank you again for joining us, and keep on exploring with New Horizons.